Okay,
Prego,
so
Sasha.
we are live now. So first of all, thank you everyone to be here. Okay, I'll try to do this. Okay, so this is the first joint seminar that we do together between the Italian Association for Community Science and the AEI SB, which is today represented by Floriana Grasso. So welcome to this new edition of the AI Spotlight Seminars. We have a joint list of speakers, and we will start with Marco Gori from the University of Siena, and then we have Elena Simper and Guy van der Broek. I'm very happy of this joint initiative. I want to leave the floor to Floriana for a couple of words before we introduce Marco and we'll start the seminar.
Hello, everyone. Yeah, just as a following up what Antonio was saying, so it's a joint initiative, a sisterhood between AI, Associazione Italiana per l'Intelligenza Artificiale, and the Society for the Study of Artificial Intelligence and Simulation of Behavior is a long name, AISB, which is the UK, the oldest, in fact, UK Association for AI. So we are very pleased for this initiative, and we look forward for the seminars to come. And sit back in my background now.
Okay, so far so good. I think we can introduce our speaker that actually really doesn't need any introduction, but we will do it anyway. So please, Luciano, you can introduce.
Hello. So can you hear me?
Yes.
Okay. So it's my pleasure to introduce Professor Marco Gori. He is a professor in computer science at the University of Siena, where he leads the Siena Artificial Intelligence Lab. And he also has a chair at the University Côte d'Azur in Nice. So his research interests are in the field of course, artificial intelligence, with particular emphasis in machine learning, neural network, vision, game playing, and so on. He was, I think, one of the first Italian researchers in the 80s, end of the 80s, that start publishing works in neural networks. He did some joint work with Joshua Bengio and Renato De Mori. Since there, I think he influenced quite a lot the artificial intelligence research community with many novel and challenging ideas. He recently wrote also a book that summarized his vision in machine learning and artificial intelligence. He also greatly contributed to the formation of many young, I think that 3 or 4 generations of Italian researchers in AI. And we have to remember also that he was one of the early president of the Italian Association of Artificial Intelligence. In the last year, he was interested in integrating, in finding an integrated model, computational model for reasoning and learning. And he is proposing novel models on computation of the relationship between the relationship between human brain. From what I know personally, Marco, from my personal experience, I can say that he was really a very inspiring and motivating person. And he was really, and I want to publicly thank him for his contribution to the entire artificial intelligence science. Marco, stage is yours.
Yeah, thanks a lot. Thanks a lot, Luciano, for this nice introduction. Of course, I'm really pleased to be here this afternoon and to have the opportunity of giving these seminars. Frankly speaking, I'm honored to give this talk because it's simply, first of all, I'm mostly talking about an idea, nothing, let's say, well established, and so it's a very good opportunity for exchanging something that let's say, more than relevant from a scientific point of view, at least as yet. I don't think there are any reasons for claiming that this is really important at this time. But you mentioned my passion in in this in the field of artificial intelligence. I really hope to deliver what is boiling inside me, right? So the passion in this activity. So you see the title, Laws of Learning. It's an attempt to reformulate learning from basic principles. There are some intersections with consciousness, but let me tell you more about what is the outline of my talk. It is mostly on these three parts, right? So the connection is wave, the framework that I call of collectionless artificial intelligence, and the role of time. So agents, which could be conscious, and the role of time. And then I will, in the second part of the talk, I will give you a few insights of on what I'm doing. What are my ideas about how to follow a path where we change dramatically the mechanism of learning. Essentially, I will show you some idea based on, inspired from principle of theoretical physics, and how these principles can help in mechanism of neural diffusions, right? And to the formulation of new building blocks in neural computation. But let me go straight to one important point, at least in my understanding. The evolution of artificial intelligence in the past decades has been, follow a path where we are seeing, for example, in the second part of the 80s of the past century, the explosion of the connectionist wave, right? This book, it's a popular book. I would say a seminal book, the book on parallel distributed processing. I think there you can find many ideas that have been of crucial importance for the evolution of learning in the past decades, right? But interestingly enough, today I want to come up with a position which is essentially that most of the basic ideas that were delivered are still in their infancy. For example, a few years ago we organized, I contributed to the organization of a couple of workshops about the mechanism of neural diffusion and learning, something beyond backpropagation. It was a NeurIPS workshop, and at the same time a workshop on biologically plausible learning, which is an issue that I think it's important also in artificial intelligence. And so going back to this book, I think, I took a few pictures from my copy. I think it's a crucial book, especially for, these algorithms of neural propagation and essentially backprop. But I very much would like, to mention a very interesting paper that I discovered by Francis Crick. Francis Crick was a Nobel Prize, the popular Nobel on DNA. And Francis Crick wrote an insightful paper on what he called the recent excitement about neural networks, right? And I think was a great paper at that time because it was pointed out some important limitations on the mechanism of learning, and particularly on biological plausibility. And for example, other people like Tommaso Poggio and others, Geoffrey Hinton himself, made interesting comments on the biological plausibility of backpropagation. And I'm confident, people who know the details of the algorithm of backprop understand, what is the essence in the biological plausibility issue. But I claim that there is probably something more serious problem, right? And a problem which is even more serious is that it's not just a matter of biological plausibility. If you look at one of the most popular model of neurons, this is a model of neurons that everybody knows. Well, in this model, you see there is the propagation of the activation, right, from the input to the output, but there is no time, right? So essentially, it makes a lot of sense once you're involved in algorithms, right? Because you calculate X as the outcome of these values of the input, right? But there is no time here, right? So we are mostly missing physical plausibility, well before the biological plausibility. And as you will see in the rest of my talk, I think this is playing an important role, especially after the recent evolution of generative AI, which is based on technology where the role of time, I think, is not as yet very well understood. So it seems to me that reframing learning in the direction of time could also lead to a higher degree of autonomy and also, toward the development of conscious models, because it is exactly, the interaction with time which make it possible to improve these qualities. So this picture is just to give you an idea of a fundamental problem that is at the moment, it's a problem that you see in most neural network machines, right? So essentially, neural networks are as yet static machines. Even the explosion of generative AI is based not on recurrent neural network, it's based on transformers, and transformers are essentially machines which at most use mechanism for processing sequences that are based on autoregression, but there is not let's say, a deep understanding of what happened in terms of time. So, for example, if you consider the classical deep network that you see in this picture, right? This is a network with 10 layers. What is important to notice is that the learning mechanism that nowadays are dominating the field of neural network is based on schemes like backpropagation, right? So you are given a teacher, a supervisor, or even, you may also have self-supervision, but no matter how you have a mechanism for propagating the supervision, you have a mechanism which, is a mechanism like this, right? You have to forward the input, so there is a propagation of the input, and then there is a back propagation as soon as you have the information on the output, right? So suppose you are processing a sequence like in vision or in language. The typical mechanism that you have to use is that you need to process the single, the single frames, the single tokens, one after the other. So you need a sort of backpropagation step for any time, right? And interestingly enough, you might consider a different scheme, like the one I'm simulating here, right? So you might think of a sort of diffusion of the activation, right? A sort of forward diffusion, and for the backward step, you might have a diffusion mechanism like the one you see here, right? And of course, in this case, if you could be able to have this kind of learning mechanism in neural networks, look at the circles where you see that both the red and the blue part is present, you could actually update the weights, immediately, right? Without waiting for the propagation, the backward and the forward propagation. So you have a sort of pipe, but as soon as the pipe is full, then you see what happens. You approach a configuration like the one you see here at time t plus 8, where you can concretely have the backpropagation for any neuron, right? So it looks like a sort of wave, a sort of diffusion inside neural computation is important in order to gain biological plausibility, but also this temporal plausibility. So this is definitely something that as yet is not really understood. Now, let me tell you what is the most important message in any case in my talk today, is that of talking about a possible dramatic change of the framework of artificial intelligence, the one that I call collectionless artificial intelligence. And I very much would like to refer to, let's say, the most popular textbook in machine learning, the one by Norvig Russell, right? So if you look at this picture, in this picture, what you can see is, these are the title of chapters. I did my best for clustering the titles, and it's pretty simple to end up with this kind of cluster, right? Because you have from one side topics like problem solving, knowledge and reasoning, planning, uncertain knowledge and reasoning. And of course, all those topics are essentially based on what we typically call symbolic artificial intelligence. And you don't really need the availability of big data collections for having this computational framework in place. So this is, let's say, a theory where you don't actually need big collections. You need at most collections of knowledge, which is something completely different with respect to data collections, right? Whereas in machine learning, you see the second cluster. Nowadays, machine learning is characterized by, the availability of big collections, which, at the end are the secret for the success, right? So what if we start thinking of a sort of collectionless machine learning framework in which you don't need, let's say, you don't need collections anymore, right? And you simply do something like what you see in this picture, right? You see in this picture, you assume that there is the typical agent interacting with the environment. So you see there is the agent interacting with the environment, there is the perception and the action. This is the classical picture from still the book, the popular book by Norvig and Russell, right? So you simply interact with the environment, and the idea is that in so doing, you don't actually need to store information. You have to be able to gain abstraction and to act accordingly, but you do not necessarily need to have, let's say, the access to big collections. You simply need to interact and to live in your own environment, right? So what about this challenge? Can we change completely the whole field of machine learning in such a way that if you go back to this picture, right, there is just a dream of next versions of Norvig Russell textbook, right, in which you don't see this clustering anymore, right? And essentially, you also have machine learning methodologies which don't need to access to big collection. They simply live in their environment and interact and and learn. Okay, so now let me go to the second part of my talk, in which I just want to give you a few preliminary idea about what we have been doing. So this is, what I'm going to present is simply, an idea for attacking the problem. And it's an idea which, of course, can dramatically change as time goes by the way machine learning operates, and especially, the mechanism for the evolution of more abstract understanding of the world. Also, the intersection with, the symbolic part of artificial intelligence. Just to give you an example, nowadays we have this field of neurosymbolic reasoning where you have this nice interaction, for example, of logic and learning. But of course, in this framework, the saying makes sense, but we need to emphasize the role of temporal logic, right? Because you have mechanisms in which agents learn as time goes by, right? So essentially, they learn gradually. So it takes a lot of time for developing abstract notions, right? So you have a sort of developmental learning mechanism. So what is the basic assumption? The basic idea is that, if time has to be the protagonist of learning, well, we can simply notice that time is already the protagonist, for example, of physics, right? So in physics, people can very well understand the regularities, and they, have already a lot of, I would say, more than experience is their life, right? They can understand, the word of, they can understand the universe, right? The law of the universe, and they can capture regularities simply, by some theories that try to understand these regularities by taking into account the protagonist, which is time. Not all, but most important laws typically deal with time, right? So, of course, then you have also physics laws which, work concerning static framework, right? But time is definitely a protagonist, right? Can we really get some secret from physics for doing something similar in cognitive systems? My understanding is that this is possible, and this picture was the first inspiring picture, at least for me, years ago, when I started to with this intuition. It was a time in which, frankly speaking, since I don't have I just have an elementary background from physics, I had, I had this intuition, but I had to study, right? So I started to, study better, these principles, because my intuition was that, for example, the popular least action principle in mechanics could inspire something parallel in machine learning. And the reason is quite simple, right? Because this principle, these pictures come from the popular Feynman lecture. This principle tells you that particles, the movement of particles in a certain field, right, the gravitational field, is dictated by, the minimization of the least action. They call, well, when you have the least action, essentially the least action is dictating let's say, the movement of the particles. So Newtonian laws arises simply because you have the minimum of the action. You see two candidates, right? This is the typical parabolic movement of a particle in a gravitational field. And of course, this is an imagined motion. And, this one, the actual motion, is the one which minimizes the action. So what if also in learning, as time goes by, you have something similar, right? And so this was the intuition. And so I started to consider a sort of pre-algorithmic step. So instead of, thinking immediately in terms of algorithms, I started to think of laws of learning, and algorithms, of course, come later on, right? But then I was, and I'm primarily interested in understanding whether it's possible to formulate some laws of learning. And if you look at this table, you can see that there are some very nice analogies. So, for example, think of the analogy between the position of a particle and the weights of a neural network, and think about the velocity of the change of the weights of a neural network, right? So the velocity of the change of the weights is definitely important during learning, right? And so you may have an action in physics, but you may have an action also in cognitive science, right? And then you may have, as you will see, a Lagrangian term in physics, but also, in learning. And so there is a lot of, a very interesting mathematical apparatus that can be used also in learning. It was my intuition, right? But if you look more carefully, what happened in physics, my early remark was that, for example, look at this very simple problem where you see a mass and there is a spring, and this is the action. You see there is the kinetic energy minus the the potential energy which come from the spring, right? And interestingly enough, when you determine the minimum, well, it works. But in machine learning, the intuition is that you very much like to have this sign here, right? Because in machine learning, what you typically have are regularization terms, and then you have some loss function, but we don't see the minus, right? So I started to become very attracted by this difference that we have in physics, and whereas in learning, it doesn't make any sense. And you can realize that if you essentially use the plus here, you don't get the physical laws actually. So it's interesting, right? So this is one of the few things that now are very clear in our lab. Essentially, we can begin from this fundamental principle in physics, but there is something which has to be better understood. For example, these are laws, at least the foundational laws like the one I was mentioning, are based, they refer to reversible laws, right? But for example, there are some very interesting criticisms by Ilya Prigogine, a Nobel Prize, who made important contribution in dissipation, on the pure Hamiltonian view. And in machine learning, it makes sense to consider this criticism very seriously, and we can actually define a mathematical framework for better understanding what happens. First of all, there is an important thing that we have to understand, right? All the theory on optimality, beginning from dynamic programming, right? So, for example, people with education in computer science know how important is the principle of optimality, the Bellman principle, right? It is at the basis of algorithms for graph. Think about, the Dijkstra algorithm, right? At the same time, the principle of optimality is important in variational calculus, in optimal control. But the point is that this is a principle for obtaining the optimality when all the information are available. But in learning, and if you really want to think of a machine living in its own environment and learn and interact, you cannot enjoy the access to the future. You can only have the past information available, right? And so I coined this principle of causal optimality, and a causal optimal policy, is a property such that, past decisions cannot be changed, right? So essentially you process the information, but since you cannot store information, you cannot change your past decisions, right? You have just to, take the privilege of interacting with the environment, but you cannot store information, and so the decisions have to be based on the current state and the information available at that time. So, for example, one of the few things that now are very clear, is that we can reformulate the basic theory that is used in theoretical physics, and now it's possible to have a sort of what I call a sort of right action for machine learning. So essentially, you may have a plus right here, okay? And so it's possible now to come up with formulations which are strongly linked with optimal control. And one important thing, for example, is that we can formulate laws of physics, laws of mechanics, simply in the framework, in this new framework that we have been designed. And essentially, it's possible to produce the laws of mechanics using a formalism which is very close to the one that is used in theoretical physics. But the difference is that we are now using a concrete theory of causal optimization. And what is nice is that, for example, if you look at the derivation of from the Lagrangian and also the Hamiltonian, at the end, we reproduce the Newtonian laws. For example, look at the Newtonian laws, these Newtonian laws, right? Once you are given a potential, simply by flipping the sign of the Hamiltonian, sorry, it's not in this equation, but in this equation here, where you have the Lagrangian multiplier, the so-called cos theta. And this is interesting for the formulation of learning, because in learning, we don't have the privilege of observing the future, right? And so it's interesting to see that also in physics, it's possible, to think of the formulation of Newtonian laws exactly in the same way as in machine learning. So essentially, you reproduce the laws of mechanics by using this different philosophy, right? And essentially, look at this picture. There is an intriguing duality, right? So you are given an action, okay? So you have a kinetic energy and a potential energy. This is true in mechanics, and in learning, the analogy is the following. From one side, in mechanics, the laws of mechanics requires the kinetic energy, and in learning, this can be interpreted as sort of regularization term, right? So this could be, for example, weights of a neural network, and you may, promote a process of learning where you have a quick, you penalize, very quick movements, right? And then, likewise, you have the potential energy, and the analogy in machine learning is the loss function. So you are exactly in the same situation that we are in statistical machine learning, the only difference being that the average now is over time, okay? So you have to minimize a loss function, which is essentially a potential energy, and then you have a sort of regularization term. But you see the sign here has to be the right sign, has to be plus. That's why we need also, to change the foundation, the theory. And what is interesting is that all the field of learning does require, from an energetic point of view, a sort of dissipation. So we have to use some dissipation. Just to make a few comments before closing my talk. There are in the formulation of these theories, there are at least three important points. One is the construction of a theory on dissipation and irreversibility. Learning is an irreversible process. Then a theory of optimization, but causal optimization. And the other important thing which emerges is the presence, the importance of conscious actions. I think it makes a lot of sense because you may have a machine which is optimizing his behavior by interacting with the environment. But one important thing is that the machine has to be, if it is in a fully immersed in time, it makes a lot of sense that there is a sort of control of its own actions, right? So the control, there could be a sort of conscious control, right? So for example, suppose this is a machine which learned to play guitar. It is not always the case that the machine has to play guitar. There are circumstances in which the machine can take the initiative of playing guitar, right? But not always, right? And there is also the possibility of establishing a sort of self-conscious control. So you have a block which is based exactly on the same theory, which is a block on is a sort of conscious model, right? It's the block which control the operation of the machine. And then, of course, you also have a model where you essentially define the objective of the machine. There is a sort of genetic injection of the objectives, but then this conscious module is definitely integrating and controlling the action of the machine. So let me quickly surface the essence of the theory. The essence of the theory, you see, consists of replacing the foundations of machine learning, where instead of having the typical ensemble average in statistics, you have an average over time, okay? But then, that we can take into account a lot of theory which is available, for example, in the framework of dynamic programming, optimal control, differential games, and a lot of theories in physics, where suppose this is a model, okay, and this is now your risk function. You have to minimize the risk function, and this is your model. So this is essentially a neural network, okay? And the problem is that we have to minimize this risk function. So this is the typical framework of machine learning, the only difference being that now is defined over time, and there is no accumulation over collections, right? Here I'm using the continuous models, but of course we could use discrete-based models, right? So the time could be discrete time. And of course, this makes a lot of sense when you start implementing algorithms, right, and systems. But in order to understand this pre-algorithmic stage, I think, the continuous description is probably simpler. So, for example, in recurrent network, you see, in recurrent neural networks, this is a typical model of recurrent neural network. So you are given a neuron, especially for people who are familiar with recurrent neural networks. So you see there is a neuron, and essentially, the changes of the activation of the neurons is dictated by, a differential equation. When you discretize, of course, you have a difference equation, okay, instead of a equation, which is more popular in machine learning, but the idea is exactly the same. What is important now is that if you look at the connections, now you don't have a directed acyclic graph. You may have cycles, right? And cycles are definitely important if you really want to have memory of past events, right? So what is important is that as yet, if you look, for example, to all the technology that is available nowadays on large language models, the memory is in the connections, right? So you know that in order to run technology nowadays, people is counting, for example, the number of connections in those models. They are talking about trillions of connections, right? But what is important in recurrent neural network is that you can store a different kind of information in the neurons in the activation, and not only in the weights, but as you know, as yet, this is not the kind of approach that we are following, right? And mostly because we are working under the umbrella of statistics, right? And so this could be a classical model where we see also some parameters that are important for focus of attention. And then you have a risk function, right? So you see, this is just like in physics. You see again, there is a sort of velocity here. This is the velocity of the connections. You see this parameter, there is a mass and you have a potential, which, in machine learning is a loss function, and you have to minimize, this risk function. Okay, so kinetic energy, potential energy, and environmental interactions. Okay, and what is important is that these parameters, for example, the mass and these phi parameters, they are from a physics point of view, they are dissipative parameters. They play an important role in learning. So especially for people who are familiar with the specific details of how learning takes place in neural network, here is a picture which I think can give you a few insight of the importance of borrowing this mathematical apparatus from theoretical physics. What is important here is that this is the model of the recurrent neural network. You see there is a propagation from the parents for calculating the activation. But then what is important is that what is called delta error in neural network here is a Lagrangian multiplier, is the so-called co-state, for example, in optimal control. And you have laws that this time are local. Remember my comments on locality and the similar paper by the similar paper by Crick, okay, who was claiming that there are problems with locality. Here there is locality. So you have that the update only take into account children and parents. You see children for the computation of the activation and parents for the so-called backpropagation, right? So there is no backpropagation anymore. So that's the difference. So if you go back to the previous picture, you see if you take any of these neurons, what is very interesting is that you have a forward step, right? And so the forward step again involves the parents, and the backward step involves the children. So that's where there is the big difference, in this theory. Okay, so the locality of the process. So let me go. So let me skip this slide. It was just for just anyway, just in case some of you are familiar, with the details of algorithm like backprop, you can recognize that there is exactly the same spirit. The only difference being that now, this is entirely local, right? So just to, these are the previous equation, and everything is entirely local with respect to what happens in static networks. So let me draw a few conclusions. The most important conclusion in this talk is probably the comments, the two come from these two comments, right? The rest is something which, frankly speaking, is simply at the moment something I fallen in love with, right? But the first two items I think could be interesting for maybe for many of you, right? I think I invite you to think carefully about what could be the meaning of the introduction of a completely different paradigm where you think of a sort of collectionless artificial intelligence, where you move the emphasis on environmental interaction and you assume, remember my picture on Norvig Russell textbook, you assume that there is no clustering anymore concerning the title of the chapters, right? So essentially, you don't need in this new framework, in this new approach, you assume that you don't need anymore the access to big data collection, okay? But you simply access the information as time goes by. So this is a framework in which time is the protagonist. In principle, you have a higher degree of autonomy. There is the emphasis on focus of attention. There is a focus on the importance of developing a sort of developmental ability because clearly, no matter how you deal with this different environment, it makes a lot of sense to think of a sort of parallel with developmental psychology, right? This is a framework in which you can easily understand that no machine learning theory makes sense, which don't respect the complexity of the interaction with the environment. Just to be more explicit, what I am claiming is that as soon as you assume that there is no big collection available, then you cannot rely anymore on the important properties of stochastic gradient descent, which make strong assumptions, strong probabilistic assumptions, right? You don't have such a privilege when you interact with time. And so you have to think to something completely different. And one quite obvious comment seems to be that you need a sort of gradual process of learning. So these are the two most important comments. Could be the case that for the years to come, a different approach to machine learning arises, which more deeply integrate, the essence of other components of intelligence, where you don't really need to have a storage of data, right? At least in nature, we don't have such a storage of data, right? And so also from a technological point of view, that could change dramatically the mechanism behind the machines, right? Because you could have smaller machines, you may not need... Yes, you could get rid of big cloud computation, and machines could learn in their own environment. There could be a closer interaction with humans, okay? So something completely different. Well, the second part is something which, has to do with what I'm doing concerning, this challenge. And frankly speaking, is preliminary. We have some interesting and promising result in the lab, but at this time, it is only, let's say, a primitive approach. What seems to be very interesting in any case is that this framework that we can see that I briefly presented today has the privilege of showing you again the most classical neural computation in an extended form. And I just want to mention, this local spatiotemporal propagation seems to be a great replacement for backpropagation once you have this temporal learning environment. And of course, this has to be carefully integrated. And so it's, once again, a very preliminary step. So thank you so much for your kind attention.
Thank you, Marco.
Thank you. Okay, so it was a very interesting talk. I remember that it is possible to post questions to the speakers also in the chat. In the meanwhile, I will ask if here there are questions among us, Floriana, Giuseppe, or Luciano.
I have a question, clarification, if possible.
Yeah, sure.
Okay, so Marco, thanks first of all for the presentation. I'm wondering, how can you connect your ideas and your approach with what people is doing to solve the problem of catastrophic forgetting in continual learning?
Yeah, okay. Well, this is something very specific and interesting. Yeah, it's one of the crucial one of the crucial problems nowadays for people who you are mentioning lifelong learning, right? Is
Yes.
trying to use one task after the other, right? Because that's what is mostly done in the community of lifelong learning, right? So I also want to take the opportunity of this question for telling that the lifelong learning community is doing, in most cases, something which is a bit different, right, with respect to what I was proposing, because here, there is a proposition for let's say a dramatic change of the paradigm, right? Because you assume that you are a machine living, a small toy. So I'm not thinking, of course, of complex machine, right? I'm thinking of a small toy which comes in life to the environment. There is some injection of from a genetic point of view, and then the machine has its own capability of interacting, right? Even a sort of conscious approach, right? But going back to what you were saying concerning catastrophic forgetting, and especially what happens in lifelong learning. In lifelong learning, there are analogies, because, of course, lifelong is something which makes sense in this framework. The framework in the literature, in any case, the community of lifelong learning is mostly interested in the acquisition of tasks one after the other, right? So essentially they say, okay, now I'm capable of solving this task. I'm using the traditional umbrella of statistics, and I can learn, for example, to recognize unwritten characters. And then later on, I decide that I want to learn something more. For example, I want to learn also the charts, not only, the digits, right? And something more and more and more. How can I prove that there is a possibility of exhibiting these cognitive qualities without forgetting what I learned earlier, right? So in what I presented today, there is nothing which is directly, in addressing this issue, but I can tell you something about this, right? And my understanding is that as yet, for at least to the best of my knowledge, there is nothing significant in the for what I know concerning catastrophic forgetting. There are, of course, smart people who can compete on specific benchmark, and of course they show their ability, their technical ability in solving, and comparing specific problem. And there is this challenge, but the problem is there, and there is a very simple reason why the problem is there. The problem is there because it is strongly connected to the way, learning takes place in neural networks. In neural networks, what you do is that you simply, modify the weights during learning. And when you have another task, you essentially modify the weights again. What is interesting is that you don't have let's say, a clean theory for avoiding to rewrite on those weights which were crucial for exhibiting good performances in the previous task, right? So the risk is that you rewrite on part of the neural network which were very important for solving the first task. And this is catastrophic forgetting, right? Because you essentially learn something new, but then you forget the past, right? Well, what I presented today, of course, I can tell you that this is one of the topics which is a top priority, in what you have been doing in the lab. But I didn't say anything today concerning this. What can you do? For sure, you cannot use the model I was showing here. So remember, for example, look, this is a model. The only difference is that is a recurrent neural network, right? But nothing where there is this possibility of attacking deeply what you were addressing, because the issue of catastrophic forgetting, as I said, has to do with rewriting on the weights. So you need mechanism for avoiding since from a theoretical point of view that you don't rewrite in some portion of the weights, right? And well, what I can tell you is that we are using a sort of gravitational metaphor for attacking this problem. Just a couple of words for just to see whether I'm capable of giving you the intuition. The intuition is pretty simple. Instead of having recurrent neural networks where you have weights from one neuron and the other, suppose that the interaction is based on a sort of notion of distance, right? And then you have a behavior with the neural propagation of activation, which takes into account the distance, just like in gravitation, right? In gravitation, what you know very well is that there is no interaction, no gravitational interaction from planets or from bodies which are very far away in the universe, right? And the same, can be actually implemented in neural networks. So you can think of the design of proper recessive fields where, they are somehow similar to bodies in gravitation. And essentially you assume that whenever they are far away, the change of on a recessive fields doesn't essentially affect the change on other parts. And this is a way for, at least in principle, there is the basic principle for addressing catastrophic forgetting. But frankly speaking, is only I want to make sure that is only a very preliminary idea, and we don't have any evidence as yet for claiming that this is working, this is successful. Just to be sure, right? That I properly answered. So it's an intuition, is what we have been doing in the lab, but we don't have. We are still working on this.
Thank you, Marco. There are a couple of questions from the chat. One is from Emanuele Marconato, which asks, which tells, well, from the equation in the Hamiltonian formulation of learning, it seems that there is no stochasticity. So could it play a role in the picture, or is it just artifact of the optimization?
Oh, yeah. I think it's it's an interesting issue, right? It's an interesting question because you're right. It's a truly deterministic framework. And let me show in any case one slide where it is a full deterministic, apparently, a full deterministic framework, but I invite you to look at what I wrote here. Let me see whether I can find the slide, but in any case, let me tell you what is the point, right? Well, okay, maybe I need to, okay, let's go directly on the equations, right? Okay, here. Yes, let's go here, okay. Yeah. If you look at, for example, these equations, right? Apparently, everything is deterministic, right? But look, what happens is that here you have an input from the environment, and then you have neurons, right? Neuron computations. So, for example, the Hamiltonian that you construct from this Lagrangian, you see the Lagrangian has a dependence on the environment. You see, this is time, but there is also an internal dependency. So I didn't explain, what is the actual role of these variables, right? So here there is a very high degree of stochasticity in the learning process, because what I didn't explain is one fundamental thing that happens in learning, right? In learning, you see what happens. When we use this approach and we optimize, this function, the typical role of these dissipative parameters is that of let's say, interacting with the environment and changing, the shape of this loss function, right? So you see, they are functions themselves of time. So they modify you see, they essentially modify the loss function. So apparently there is no stochasticity, because the approach is based on traditional Hamiltonian functions. But first, there is a causal approach in optimization. But most importantly, in going straight to the question, there is another learning component which I didn't explain in this talk, and is the learning component which involves these dissipative parameters. So the idea is that you are given a sort of loss function, right? A Lagrangian, actually, from a technical point of view. But the Lagrangian function modifies, is changed during learning, right? This has also to do with my previous comment on the importance of having a sort of gradual learning, right? So remember, during my presentation, I was emphasizing the importance of devising policies for protecting somehow the agent from a sort of information overflow, right? So there is an intervention on these parameters, the purpose of which is exactly to prevent the agent from this information overflow. And this can be done on the basis of the energy of the system. So we have policies for learning these parameters which change completely the picture, the deterministic picture, right? So again, I was quoting Ilya Prigogine concerning the approach of the Hamiltonian approach. Of course, the Hamiltonian approach is not adequate for dealing with, in itself at least, is not adequate for processing, for modeling a framework where you have this parameters.
Okay, so there is another question from Paolo Traverso, which asks about the relation of your work with the idea of neuro AI, in particular the idea by Zador, which is mentioning a critique of pure learning and what artificial neural networks can learn from animal brains.
Oh, sorry, could you just repeat better?
Yeah, so in this question by Paolo Traverso, he asked about the relation with the idea by Zador in his work, A Critique of Pure Learning, and what artificial neural network can learn from animal brains. So what are the relationship within, if any?
First, I don't know the paper, but I understand, I think I understand the question, right? So as far as I understand, is the relation with animal brain and biological brain, the mechanism of learning, because of course, since I'm involved in time, and I'm involved in also a sort of potentially a sort of comparison with what happened, for example, in nature with any kind of animal involved in learning, right? The connection is metaphor, since when we had the first connectionist wave during the mid-80s, were strongly, addressing the comparisons with, learning in animals, right? And so the biological learning mechanism. But, I'm strongly on positions like the one I was mentioning. Remember the criticism by, these criticisms by Brick, right? By Crick, right? Who was saying that there is no biological plausibility, and also this algorithm that and this mechanism that I presented has nothing to do typically with what happens normally in the brain. There are some intriguing, very interesting analogies, right? And the analogies, of course, are in terms of connections, are in terms of also representation. But the big issue is that, we don't actually know, we don't have the possibility of borrowing detailed solutions from biology. I know this is probably an extreme position. Mine is probably an extreme position, but I'm not convinced there is much room for, let's say, understanding the details of biological processes and then to move them in artificial neural networks. There are some room and literature, but frankly speaking, what we see nowadays is based on algorithms that have nothing to do with what happens in the brain, right? For obvious reason, because it's still an open issue. Many people, I understand that they have a different, and I totally respect the different position. My understanding is that we really need to have something which is fully under the control of, math, and then otherwise you cannot control the software, and you can control, the whole system. And in this framework, I don't gain anything with respect to what we have in neural network. The only big difference is that I gain the analogy that we process over time, and we don't have a storage of information. This is the big difference, right? So essentially, we don't need to have a storage of information. But the mechanism itself is under the, let's say, some artificial models which are different with respect to, clearly different with respect to biological models.
Yeah, so thank you for the answer. If I may just say jump in I have a comment which is related to your last answer. Indeed, I mean, I was thinking that what you have proposed is actually very let's say implausible from a biological point of view, because so you are actually, if you understood correctly, suggesting that we may have agents without memory, right? So in addition, I have added conscious agents without memory. So, but memory is, on the other hand, a very important element, because you mentioned that you would like to avoid completely this notion of storage. So, did I understood correctly?
Yeah. Oh, okay. Thanks. I think this comment made me the opportunity of clarifying an important point, right? The approach is promoting something, regardless of what I'm doing here, right? I'm promoting something which is completely orthogonal with respect to what is done in machine learning. And it can be explained in a very simple way, right? Your challenge is to, design toys, the purpose of which is to exhibit some relevant cognitive process, but you don't have the privilege of storing data. When I say you don't have the privilege of storing data, I'm assuming that, for example, for example, right? We have this, in this afternoon, I had the honor and the privilege to give my talk, right? And so there are some people listening to this talk. They will be, somehow, they will develop their own idea, right? Their own abstract interpretation. But of course, none of them, no one will be capable of storing the video, right? If you really want to store the video, you need a computer, and from a formal point of view, you have this information which is available under the theory of communication, right? The sampling theory. Then you can store information, right? And storage, when I say store, I'm mentioning this kind of storage. Please bear in mind that no neural network at the moment, no large language models, no technologies of AI, right, is available without the technology of storage of data, right? When I'm talking about storage, I'm referring to this requirement of, producing huge collection of data, which is fundamental for the statistical framework of the machine learning algorithms to operate. Otherwise, they can't, at least as they are designed nowadays. The framework I'm proposing is something where you don't need such a collection anymore, which is totally different. Going back to what it means, memory in machines, that's a different story. And that's a different story simply because the machine can store, can create an internal abstract representation of the world, the environment, in the connections. And not only in the connections, it is what is already done, right, in our neural networks, right? You have an internal representation in the connections. In recurrent neural network, you have an additional level because you can store also information in the neurons, right? Just like flip-flops, for people with education in computer engineering. It's like the difference between, let's say, combinatorial switching logic and sequential switching logic, right? When you have the flip-flop, right? So there is this possibility also of producing this abstract representation, but it's a sort of compressed representation of the environment. It's not a video of this talk, right? And these machines, the challenge for this machine in the collectionless AI framework is a challenge where the objective is that of devising and developing an abstract representation, right? So not to store, right, but to develop an abstract representation from their life instead of from a collection, right? So this is where the challenge is. For example, remember the comment by Luciano, the previous comment by Luciano. He was asking comparison with lifelong learning, right? Lifelong learning in most of the literature nowadays is not a field where you are exposed to the challenge of learning in the time direction. You are essentially trying to do your best to prove that you can learn one task after the other, but you are still under the umbrella of statistics and you have still some categories of machine, right? But there is for sure there is a storage, right? From a cognitive point of view, of course, memory is crucial, but memory, the memory that also we human develop, is far away from the memory of that you can produce from a video, right?
Thank you for the clarification, Marcos. There is another, and I would suggest that this is the last question from the chat. So that is coming from Francesco Balzan, that asked for a comment on the work pushed by Carl Friston on the and the active inference community on bridging natural and artificial intelligence.
Yeah, well, I personally met Carl Friston, and I know he is one of the most cited and inspiring scientists in this field. I know some of his work, I would say quite superficially, from my knowledge, which, as I said, is quite superficial. My understanding is that he's doing something which is different. I never seen this kind of straightforward position of the problem. But of course, I'm confident there are some intersection. I confess again that my knowledge of his studies is not probably enough detail, right? He wrote an impressive number of papers, and but for what I understood, there is not this straightforward challenge that I'm proposing. And again, just to reinforce what I was saying, please be separate the insight on this new potential framework of collections AI and the few and preliminary studies that I presented in the second part of the talk. It could be the case that, as mentioned, studies by Carl Friston and of others, are somehow also going in this direction.
Okay, so I just would like to say on behalf of all the committee, thank you again to Marco for this really great talk, and we learned a lot from you, and looking forward to the next steps that you and your lab are doing on this.
Thanks a lot for having me this afternoon and for the opportunity I had to. Thanks a lot. Thanks.
Thank you very much, and so see you in a couple of weeks with the next seminar.
Ciao, bye.